just hitting record now. Okay, so firstly, what is the name of the law that is under investigation? The hint would have already been out, but as I said, just be careful and make sure you look at what is being kept constant and what is varied. If pressure and volume, PV, is varied, and your temperature is kept constant, then definitely it is Boyle's law. Okay, so the first one is definitely going to be Boyle's law. Write down a suitable investigative question. So I'm just going to give you guys the long version, just in case there are awarding marks for including everything. But it's basically standard, right? If you learn the investigative question for Boyle's law, it's going to be the same all the time. So it's going to go something like, what is the relationship between the pressure and volume of an enclosed gas at constant temperature? And don't forget your question marks. So again, just reminding you about how they mark these things. Where you get your marks here is firstly if you've included both these variables. So you've included pressure and volume as being changing. And sometimes they might give you a mark for saying enclosed and constant temperature. The two variables kept constant. But obviously you have to have it phrased in a question. So using the word what, or as long as it's a question, you can't write this as a statement. Okay, 9.3 is to give a reason why the investigation must be conducted at a high temperature. Okay, so this one requires a little bit of thinking outside of the box of what is actually going on here. So let's look at the theory we've been doing previously as well. We are running an investigation where we've got gas, we've got pressure, and we've got volume, and we are basically looking at the relationship between the two of these. We're looking at Boyle's law. Okay, and the special thing about all these laws we're going to look at is that they are actually assuming that we're dealing with an ideal gas. So they want us to be dealing with an ideal gas. And as we said previously, there's no such thing as an ideal gas. We have a real gas. But the best we could do is we could take the real gas and we could get it to be as close as possible to the ideal gas. So that's a very big hint here, right? And what you'd realize is that in order for a real gas to approach the ideal gas, or to become like this ideal gas, you have to have a very high temperature for this. And if you remember why, think about your intermolecular forces. If you've got a very high temperature in your cylinder or wherever the gas is, let's think about what is going on there. This is your cylinder, and here's your particles inside, and I apply a very high temperature to these particles. They're going to vibrate, they're going to move around a lot, right? The space between them is going to increase. And most importantly, what's going to happen to the intermolecular forces? What's going to happen to the glue between them? Isn't it going to be very, very loose? It's going to be very weak, and that's what we want, right? So we have a high temperature to ensure that we have no intermolecular forces. So that's just the thought processes, but I want you guys to see that, right? So we want the real gas to approach the ideal gas, and we have to have a high temperature for that because we don't want intermolecular forces interfering. And to sum up everything, the last thing you would have to say here is that this is to prevent, let's think about if you have a pot of boiling water on the stove. We have to apply a very high temperature to the water. And I already used that word, but what is basically going on in that water is that it is boiling, right? It's reaching an ideal gas. And if we were to lower the temperature, something is going to happen to that gas. Isn't it going to become droplets of water and it's going to fall back into the pan? And that is condensation. Condensation is basically the changing of evaporated gas into a liquid, right? Going from a gas to a liquid. So this is also to prevent condensation. From occurring, right? But again, as long as you explain this properly, then whoever's marking your paper should see that, you know what, you actually understand why we need a high temperature. And sometimes they do this in physics. They'll, like in the memo for this one, this was the answer they've included. And some other paper, they might have a different answer. But the point is, if you understand the concept of what's happening here with the intermolecular forces, your teacher should honestly give you that mark. So I always like to say, explain yourself well in points. Don't go on writing paragraphs, but explain in main points what is going on, and then they should be able to see you understand what's going on here. Okay, but again, main point is to prevent condensation from occurring. All right, so let's move on to 9.4. So we're saying now, from the results obtained, the first volume reading A is correct. Let's highlight A. So A is the first volume reading here. They're telling you that that one is actually correct. So we can trust that reading. While one of the remaining volume readings is actually incorrect. So obviously it's going to be either B, C, D, or E is going to be incorrect. And they want you to actually go and choose from this. And 9.9.2, let's just carry on reading. They want you by a means of calculation to determine what the correct volume reading should be. So let's start off with 9.9.1 and firstly find out which reading from B, C, D, or E is incorrect. Okay, and you have one correct reading. That's the hint, I'd say. So I'm going to give you guys some time to think about this one carefully. Try 9.9.1. Yeah, just do 9.1, 9.1, and then when we're done with that, we'll move on to the second one. And your hint here is, remember, we've only done one equation, and you know one of the correct readings. So using that information, you now need to find out which reading is incorrect. So I think before you guys even attempt it, just to make sure we're all on the same page, let's just all think about what method are you going to use. So before you even answer that question, I want you guys to think about what method you're going to use to find out which answer is incorrect. And once you have that method, in the next 2 minutes, we'll talk about that first, so that everybody's on the same page and we can all go ahead and find that incorrect answer. Okay, so I'm going to stop you even if you started finding that incorrect answer. We're just going to stop and talk about what thinking and what method should you use to firstly find that incorrect answer. So it is a bit of an application question, a bit different from, the usual straightforward questions where you know what to do. This is now testing how do you understand this investigation. So let's take it a step at a time and let's discuss what we can do here. So the first thing I want you to focus on is, remember, we know that reading A is correct. So we're going to highlight that in green, and that's going to be our go-to. If we need to compare anything, we're always going to use reading A because that is a correct reading. And next we know that, let's just read again the introduction that we have. We're looking at the relationship between pressure and volume, and then the researcher is varying pressure. Okay, so in other words, what this means is the researcher has control over the pressure. And you can see that clearly from the table. If we look at the readings on the table, it's going very nicely, 15, 20, 25, 30, 35. Okay, so we can kind of trust these readings here as well. So I'm going to highlight those in green as well. All right. The problematic readings is going to definitely be the volume. Why? Because they are recording the volume here. So these values, we don't know if we can trust them, right? So I'm just going to put a circle around that. So that's enough information now to get us started. Now they're telling us we now need to go and find that incorrect value. Okay, so what information do I have coming into Boyle's law? I know that, I'm just going to write it at the bottom here. I know that P1 V1 is equal to P2 V2. And what this law tells me is I have to have at least two states. So I have to have readings for state 1 for pressure and volume. And I have to have readings for state 2 for pressure and volume, right? Let's go back to the table and let's see if we have that. Do I have a set of readings for state 1? Well, I know that for reading A, I've got a pressure value and I've got a volume value. So I can put a tick here and I can use reading A for this, right? So I'm just going to highlight that in green. What about state 2? So for state 2, what I want you to notice is that all the green readings is what I can trust. I can use those values. So I can actually use 20, 25, 30, and 35. So those are going to be values that I'm going to start putting into pressure 2. But the volume values I cannot trust. So what I'm going to do is I'm going to use this equation. I've got 3 values that I know for certain. Volume 2 is something I do not know. So I'm going to use this equation to check this value. And if the value I get from the equation matches what's on the table, that means that it's a correct reading. If the value I get from the equation for volume does not match the volume on the table, then it means it's an incorrect value. Okay, I just want to explain this a bit clearly using just 2 values in case you are getting confused. Let's just quickly go through it one more time. We know that we've got an equation. P1 V1 equal to P2 V2. I need at least 2 pressure and volume values for state 1. Where do I get those values? I simply get it from reading A because I can trust both of those values. So I'll put in the value for pressure here as 15. I'll put in the volume here as 160. Why I can trust that is because they told me it's correct. Okay, and then the next thing is, let's go on to reading B. I can trust the 20 for pressure because of this point here. The person is varying the pressure value. Okay, so that means it's a correct value. So I have a value for pressure, and it's coming from that table. It's going to be 20. And then how this equation works is you've got 3 values here, which means we're going to find V2. So if I plug in everything here, I'm going to find a value for V2. Right, I'm going to get some answer here. If this answer here corresponds to 120, it means it's a correct value. If it does not correspond to the 120, it means it's an incorrect value. And then now you obviously have to do that 1, 2, 3, 4 times. And then you'd finally see that out of the 4, you should get 3 correct and 1 incorrect. So I'm going to give you guys some time to quickly try that. And then in 2 minutes, we'll mark that. If that is confusing you in any way, again, please stay back at the end of the lesson and we'll talk about it. Okay, so I'm going to attempt the question now just to save us some time as well. I'm just going to repaste it here just so we can have some space on the side. Alright, so what are we doing? We are doing 9.9.1. We are finding out which value is incorrect. We can trust reading A, we can trust all the pressure readings. So what we're going to do is we're going to start off, I'm just going to call it, we're going to start testing reading B. Okay, the equation we're using is P1 V1 equals to P2 V2. Now remember that these are just subscripts, right? I can replace that with the letter that the reading rather that I'm using. So for instance, I know I'm plugging in pressure A, volume A, and I'm testing for B, so it's going to be pressure from B and the volume from B, right? Let's substitute. So for pressure A, we've got 15, and for volume A, we've got 160. For the pressure value of B, we've got 20, and we are finding out what the volume of B is. If we do the maths here, we are basically saying 15 times 160, and we're dividing by 20. And if we put that on our calculator, you should get a value now of 120, and your unit should be centimeter cube. Now notice what this means for us. The 120 here matches the 120 on our table. So that means that the 120 is a correct reading. So let's go ahead and highlight that in green. That means that reading B has to be correct. Now we're going to repeat this until we find a value that does not match. So we're going to go ahead and test reading C. Okay, I'm just going to go straight now to, okay, it's fine, I'll do all the steps. So we've got the pressure from A, the volume from A, and we've got the pressure from C, the volume from C. Pressure for A is 15, volume is 160 from the table. The pressure for C is 25, and we are testing for the volume of C. You should actually get from this 96 centimeter cubed. So it matches perfectly here. Therefore, this is also a correct reading. Let's try reading D. Okay, so you've got pressure A, volume A equal to pressure from D, volume from D. 15 times 160 is equal to, your pressure from D is 30. And your volume is there. When you solve for the volume of D, you should get a value here of 80. Okay, now let's look at that value, comparing it to what we have on the table. We've got 80 centimeters cubed from the calculation. Sorry about that. 80 centimeters cubed from the calculation. But if we compare to the table, here we've got 88. So definitely this is not looking right. Okay, so we'll mark this as the incorrect one for now. But just to make sure, we'll also go and test reading E. And if you test reading E, you should find that the volume for E actually does work out to be 68.6 centimeters cubed. So this one is correct. You can mark that as correct. And then what happens here is we found the incorrect reading. It's going to be result D. Okay, but as long as you guys understand what we're doing here, that's the most important thing. Okay, and then 9.9.2 is by means of a calculation, determine what the correct volume reading should be, as identified in 9.9.1. Basically, they want the correct value that matches in the table. And we've already done that in our calculation. We found that the volume of D should be not 88, but 80 centimeters cubed. Okay, so I hope that makes sense. I'm just going to give you guys a minute in case you need to take down corrections, and then we'll move on to the next law. Okay, so that brings us to an end for the questions on Boyle's law. As you can see, there's nothing too complicated about it. The most important thing is you understand what the law says. You understand that main equation that we talked about, P1 V1 is equal to P2 V2, and you understand how to apply the questions for investigations, right? So being able to simply do things like this, and the question we did as well in our last lesson last week, that's going to be the extent of how they test you on this. Okay, but then there's not only just Boyle's law, because as we said, we're always dealing with, I'm just going to make some space here, we're dealing with pressure, temperature, and volume. And so far, we've only looked at changing these two quantities. What happens if I wanted to keep my volume constant and I wanted to change the pressure and temperature? So we definitely have other laws for this. We're going to have two more that we're going to talk about now. And the first one is called Charles' law. Okay, so Charles' law is basically now, I'm just going to write down the guideline definition. It's telling us that the volume of an enclosed gas is directly proportional to its Kelvin temperature provided the pressure is kept constant. Okay, so very similar to Boyle's law. You guys are lucky that if you understand Boyle's law and the overall idea and picture of what it's trying to teach you, the next two laws, including this one, is going to be very easy, very simple. It's just now we're dealing with different variables. So if we read this carefully, I'll give you guys a minute to take it down just after the explanation. We told you that the volume of an enclosed gas is directly proportional to its Kelvin temperature, provided that the pressure is kept constant. So a lot of different things, but I just want to draw your attention to two important things. We're looking at two variables affecting each other. The volume of an enclosed gas directly proportional to the pressure. So here now, sorry, not pressure, temperature. Okay, so here now we're looking at how volume and temperature is changing. And obviously that means, as we spoke about previously, if you're changing volume and temperature, you can't also change pressure. You need to keep this constant. So this is the variable that is kept constant. Okay, and the law also tells us that it says pressure is kept constant. And they also told you enclosed gas, which means your mass is kept constant. So I'm just going to give you guys a second to take down this guideline law, and then we will look at the equation. Remember, as you're taking down these laws as well, look at it as a time to actually just memorize it now. So the more you read it, the more you understand it. You don't have to come back before the exam and learn this law as if it's brand new. Guys, did I unshare my screen mistakenly? think I did. Nobody said anything. Okay, I think you can see it now. I just mistakenly hit that button when I was writing. But yeah, why I was quiet for so long was I thought you guys were taking down this law. But it's fine because the video also will be posted. But again, this is Charles' law. Two important things is volume and temperature. You can see I wrote down a little summary like at the bottom here. Volume and temperature is now being varied, and pressure and mass is your constant variables. So already at the back of your mind, you should be thinking in your investigation, if I'm seeing a table that looks something like this, where I've got volume and I've got temperature and I've got varied values for this, already in your mind it needs to click that this is talking about Charles' law, okay, because they are varying the volume and temperature. If you saw pressure here, then you know we are talking about Boyle's law because Boyle's law varies the volume and the pressure. Okay, so let's talk about what this means now. So the law is firstly telling you that the volume and the temperature is directly proportional. What does that mean? That volume is directly proportional to temperature. This means that if you were to increase your volume, your temperature is also going to increase. So increasing the volume increases the temperature. Decreasing the volume is also going to decrease the temperature. Okay, so a little table for us. But what does this look like now in a graph? So it's always important to understand what the shape of this graph looks like in case you have to draw it or in case you have a multiple choice question where you have to select it. So if we look at a simple graph here, volume on one side, temperature on the other axis. Alright, so if we picture it, as I'm increasing my volume values, my temperature values are also increasing. So your points should be something like this. And now for this graph, it is indeed a straight line, right? So it should look something like that. So it is a straight line. It's a directly proportional graph. Okay, and then the next important thing is what is the equation that we're going to be using for this law? So the equation for this looks something like this. And I want you guys to also see that we don't have a brand new equation here. We're going back to that equation that they gave you in your data sheet. So remember this equation here, P1 . If you remember this equation, then it becomes really easy, right? Because if we're talking about volume and temperature that is changing, but your pressure is constant, what this means is at state 1, you started off with a pressure maybe like 300, and at state 2, your pressure didn't change, it's also 300. So because it's the same value in 1 and 2, we can simply cross off this P2 value, P1 and P2, and the remaining stuff becomes your equation. So your equation that's governing you here is going to be V1 over T1 is equal to V2 over T2. Okay, so don't go and learn these specific equations. Look at the general one and just cross off any variable that is kept constant. Okay, so I think that is basically all the theory. If you, I'm going to move the slide now, but if you need to take down anything, just let me know in the chat now. I'll paste it back here. I just wanted to do one more question for Charles' law, but I think while we're here, I'm also going to do the last law, and then I can give you the exam questions also to do as homework, and maybe if we have time, we'll do it in the next lesson tomorrow. Okay, so while we're here, I'm just going to do the next law. So let's just quickly look at what we've been doing. We said we've got volume, temperature, and pressure. So far, we've looked at a case where we varied the pressure and we varied the volume, and temperature was constant. This was Boyle's law. Charles' law is the one where we varied the volume and we varied the temperature and pressure was constant, so this was Charles' law. Now, obviously, you can see which one did not have a term to be constant. It's going to be volume. Now we're going to vary temperature and pressure, and this law is called the Gay-Lussac law. Gay-Lussac, right? So you can see this is where we're going to vary pressure and temperature. So your job is just to remember these three different laws, right? They're not going to tell you Charles' law is where pressure is constant. As long as you learn how to relate these, maybe make up a mnemonic for yourself or something, and try and relate all these laws. So that if you get a table and you see volume is constant, then you know it's going to be this law. Okay, so let's just quickly talk about the last law, and then we will attempt some multiple choice questions as well. Okay, so the guideline definition for this law says that okay, they don't give you a guideline definition, so we're just going to make up one. So we're going to write it as the pressure of a gas of an enclosed gas. Okay, so this is our law for the Gay-Lussac law. The pressure of an enclosed gas is directly proportional to its temperature in Kelvin at constant volume. This table is really nice because it reminds you of everything, right? So I know it can be very confusing because we've got three different variables and we're changing so many of them. So even if you need to make this table for yourself and make a mnemonic so that you can relate the laws, because remember, in your exam question, one of the first questions will be they're going to give you the different variables and they're going to ask you to name the law. Okay, so you can't mix up the names of the law. So for Gay-Lussac, we can obviously see we've got temperature and we've got pressure that is changing, and volume is the variable that is kept constant. And they're also telling us that it's directly proportional. That means that P is directly proportional to temperature. So in other words, as you increase your temperature, your pressure is also going to increase. As you decrease your pressure, your temperature is also going to decrease. And in the same way, your graph should look something like this. It should be a directly proportional graph like this. Make sure you remember the relationship. And then in terms of the equation that we use, remember, let's go back to our first equation that we're going to get in our data sheet. The reason I'm using equations from the data sheet is because if you are in the exam and you forget the equation, always go back to what they're giving you. This is what you're going to flip your page and see. Now you need to remember the Gay-Lussac law. What variable is constant here? Volume. So I can scratch out the volume, and this becomes my governing equation. P1 over T1 is equal to P2 over T2. Okay, and that is basically all the theory that you need to understand for these three different laws. So I'm just going to give you guys a little bit of time to take this down, and then I don't think we'll have time to attempt. I had like 2 more questions left, which was exam level. We're going to attempt some of the multiple choice questions for the gas laws. Okay, so in the next lesson, hopefully I'll try and make up a nice worksheet which has a summary of all of these things so you can use it as a revision to study. But for now, as I said, we're just going to go through some multiple choice how they generally test this. Okay, yeah, so I just wanted to quickly show you this first one here of the importance of understanding that graph relationship. Okay, so here in 1.6, they're asking us which graph correctly shows how a real gas is going to deviate from an ideal gas. How does a real gas deviate from an ideal gas behavior? So the dotted line here is meant to be the real gas, and the solid line is meant to be your ideal gas. So I want you guys to take a minute and choose your answer, and then we'll talk about which one and why. Okay, let's have a look at which is the answer and why. So let's understand firstly this question. How does a real gas move away? Deviate is going to confuse you to say, how is a real gas going to move away from an ideal gas? So it becomes less and less like an ideal gas. And what do we know an ideal gas to be famous for? It has a lot of intermolecular forces. So if a real gas is moving away from an ideal gas, what can we say about it? It's going to have less and less intermolecular forces. So that's going to be the key condition here. We're going to look for a condition where we have very little intermolecular forces. That bond is becoming very, very weak. So the first thing is, let's just select which pattern of the graph is correct. So we're dealing with a case here of a real gas and an ideal gas. And just a hint is that anytime they're asking you about the deviation, it's always going to be a curved graph, all right? So that eliminates A and it eliminates C as an option. So we're left with option B and we're left with option D. Okay, so let's think about it. Let's look at what is the difference here firstly. Graph B is showing us a case. So remember again that this is our real gas, this is the ideal gas. So here what's happening in your volume relationship is that it deviates when the volume is basically higher. And you have to be able to see that from your graph, right? Remember, we're just reading a graph here. How am I doing this? How am I getting this? If I highlight this graph, that is a very big, sorry. If I highlight this graph and I highlight the ideal graph, what is the difference? If I draw my line to my volume, the real gas has a higher volume, but your ideal gas obviously has a lower volume down here. That is how I'm getting that condition. So I made a note of it. Let's look at graph D. What is the difference here? So again, remember that, let's just highlight it. So this right here is going to be our ideal, and our real gas is the dotted line. What is the difference between these two? I'm just going to zoom in. We can see that they have a difference in, not temperature here, but they have a difference in volume as well. If we draw a dotted line coming down, we can see that the ideal gas actually, or the real gas, let's talk about the real gas. Okay, so here your volume is lower. Okay, but there's something interesting going on with graph D. And I don't know if you guys realized it or not. if you look at the shapes of your graph, remember what we did at the start, right? We looked at Boyle's law, and Boyle's law talks about, Boyle's law is the only graph where you're going to get a curve. That's an important thing. I'm just going to make some notes on the side here, just so I don't confuse you. So Boyle's law was the only law where, and remember that tells us pressure and volume. Temperature was constant. This is the only graph that is going to have a curve. Any other graph, the Charles graph, the other Gay-Lussac graph, which deals with temperature and pressure, and the other one dealing with, Charles graph deals with volume and temperature, and the Gay-Lussac law deals with pressure and temperature. These are going to have straight line graphs. So that should be your first clue. Anywhere where you don't see P and V, strike that off if it's not a curve. If we look at graph D, there they're dealing with temperature and volume. Temperature and volume is the Charles graph, and we know that the Charles graph is a straight line graph. So this should definitely be incorrect. Okay, so you can scratch that out. The reason I scratched out C is, again, this is the Gay-Lussac graph. So what we're doing here is we're looking at graph B, and we're looking at the volume being higher. But the whole point of this is we need to relate it back to this condition here. Is it indeed going to have less intermolecular forces? So you have to think about that in your head. If your volume is higher, in other words, you have a much bigger container, is the bond between the molecules going to be greater, or is it going to be weaker? And if you think about that, it is going to be much weaker, because if you have a very large container, all your molecules are going to move very far apart, and they're going to not want to stick to each other. So they are indeed going to have less intermolecular forces, which means your real gas is going to deviate from your ideal gas. And this is why our answer is going to be B. You would obviously go to graph C and you would test that relationship as well, even graph A. Go to it and test the relationship, the exact same way I did it for graph B. So a little bit of thinking, but this is generally more of the higher level questions that they ask in the graph form. Okay, and then there was one more question I wanted to look at, but we will definitely not have time to do it. So maybe I'm just going to show you guys, and you can take a screenshot, or you can go back to the video and do try to attempt it, because the next time we have lessons, we're going to go through it. We're going to start with it. So have a good understanding, and it's this question here in 1.9. Okay, so you can go back to the video, or you can take a screenshot of this now, and then I want you guys to actually think about it and work on it. So with all of that being said, we are running out of time, so I will see you guys next week. Okay, you can stay back if you have questions. If not, then I'll see you guys.